we will always kind of start with quote-unquote normal feedback control being the base of any kind of control system that we're going to be working with. And then we're going to layer on additional helpful things, which usually take the form of, and kind of we've spoken about, the first kind of thing that we incorporate is measure as early as possible. Right, and this was basically feed forward. Act as quickly as possible. And this was, this led us to this technique of cascade. And today we're going to talk about exploiting knowledge of the system. And now, that number 3, you may think about number 3 as being spread out in a lot of the stuff that we've been doing in this subject. We spent a whole semester learning about developing models of systems in order for us to be able to use that knowledge in designing our control systems after all. And you may call to mind that both feed forward, so feed forward actually had a model component in it, right? So we couldn't design a feed-forward controller adequately without having at least some idea of what the effect of the disturbance is going to be. So feed-forward is always kind of like a fundamentally model-driven activity because we need the model, or at least some kind of model of the system in order to develop a feed-forward controller. But now we're going to be talking about using this in a more direct way, and specifically to address a problem, which is that dead time reduces control performance. So, we're going to ask ourselves whether it is possible to exploit knowledge of delays in designing some way of countering the negative effects of dead time. And so the first thing that I think we need to talk about is that dead time, or kind of understanding what the effect is of dead time on control performance. And so when we say dead time reduces control performance, what we mean is, given a similar control structure, an increased delay in the measurement will typically degrade performance. Or in other words, if I had a slider, and you can kind of see what I've done here, I've just simulated the same controller acting on a system. So keep in mind, this is now using the same control tuning as well. And remember that this is available on the repository if you want to go back to this and kind of look at that. It will even not contain this a little bit later today. It will no longer contain that error either. So imagine that it was like a minus from the beginning. So we've got this second order plus dead time system, and we're just using exactly the same controller. And we find that actually, if we have the original system, that original system is basically uncontrollable, or the control is very bad if we were to use exactly the same control settings, right? And so you can see the blue line over here is the original nice tuning. And I can't recall exactly how I came across this tuning, but you can see that that has a relatively nice, crisp control response. Adding the dead time, adding that delay, degrades control performance. Now, I'd like to spend a little bit of time, so that's the simulation version of this. Yesterday, when I was incorporating some of this frequency domain reasoning about why these controllers work, I felt that I was losing a couple of you. I could kind of feel the eyes glaze over as I was doing that. So I want to talk about this degradation in control performance from a frequency domain point of view so that you can kind of see, I feel that understanding the frequency response of these systems gives you a great amount of insight into, let's say, at least some explanatory insight into why dead time does this. You can start by looking at a time domain graph like this. And it's not that hard to tell yourself that when the information that you receive from a plant is delayed, your decision-making ability is compromised. So if you only hear a day after something bad has happened, that it has happened, clearly it's been bad for a day, and you can only respond to that late news. The best response cannot alleviate the fact that it's been bad for a day. The earlier you know something is wrong, the earlier you can respond, and by and large, the better your control will be. And so that kind of common sense time domain explanation, I think, is relatively sufficient in terms of understanding why delays are bad. But when we view this in the frequency domain, I want you to recall that the frequency response of this second order system we can kind of sketch that Bode diagram out, and we know that for a second order system, the gain part will typically have these two inflection points, or two places where the slope changes. We'll go from a slope of 0 to a slope of -1 per decade to a slope of -2 per decade. And so that's on the gain part. And on the phase part, having just this system, I would imagine a set of inflections roughly at the time constants where I lose 90 degrees of phase for every lag. And so so I start at 0, I go to minus 90 degrees, and I end up at minus 180 degrees. This is the Bode diagram of the system itself. And remember, I'm working just with this second order system over here. So this would be the fast time constant would be over here. So this would be 1 over 3, and this would be 1 over 5, right? Oh, sorry. So let me see if I can remove this. Let's see if it disappears. Yes. So I've got my time constants in that order. 1 over 5 is less than 1 over 3, so that's kind of the order in which they come. And for just that second order system, that thing will asymptotically go to minus 180. And I want you to remember the Bode stability criteria, or the Bode stability criterion, which, if you will recall, asked you to look at the place where the phase reaches minus 180 degrees and said, if the phase is minus 180 degrees, then the system will be stable as long as the gain at that same frequency is less than 1 for the loop transfer function. And What's cool about this system, the second order system just by itself, is we can see that we will never actually reach that frequency. There is no frequency at which we are crossing over 180 degrees, right? And kind of the magnitude looks like it just is going all the way down. So even if we could imagine touching the minus 180 line somewhere very far that way, right? That equivalent gain would be minuscule. It would be very, very small. And so we kind of guaranteed stability for any kind of gain that we can think of. And so in the frequency domain, this is an easy way to understand that first and second order systems with proportional only control have guaranteed stability. Because if for a first order system, the maximum phase lag is minus 90 degrees, and for a second order system, the maximum phase lag is minus 180, and both of those systems therefore never reach this point. We can never find that crossover frequency, and therefore we can never get to frequency, a realistic frequency where I'm looking at that gain. So, and you'll recall that when hopefully you've all watched my Nyquist or frequency domain stability video. So you've also seen this same idea on a Nyquist diagram. The Nyquist diagram for this second order system looks like this, right? So we can see that at the zero frequency part of that Nyquist diagram, if you recall that we start over here, and then larger frequencies move us from that point kind of all the way into there. And for the second order system, so remember also in the Nyquist stability criteria, we're kind of looking for encirclements of that minus 1 point. And you can see it doesn't matter how big this shape becomes, it never touches the minus 1 point because it's kind of carefully, it has that heart shape, and the heart goes to zero at minus 180 phase. So if you look at that, that's zero phase, and remember the phase is this angle over here, so going from zero phase to minus 180 phase, at minus 180 the magnitude is so small that I'm never going to get to that point. Sorry. Now, what happens when we add dead time to this picture? So the original version I'm going to leave there. I'm going to add in the version with dead time. We know, or you should by now remember, dead time is one of the frequency responses that I expect you to have committed to memory. It has no effect on the gain part. And so for the dead time version of this, the gain part is unchanged, but it has this infinite effect on the phase part. And so it starts at very small phase. And so typically we'll start there, and then adding some dead time will have that kind of pull away. And if you zoom out far enough with dead time, you'll see this just keeps going down. And so from a frequency domain point of view, this is clearly, you can kind of see that the dead time, as soon as that dead time hits, even for the smallest amount of dead time that we can imagine, if there is any delay in the measurement, we go from this crisp, never getting to 180 to getting to 180 eventually, right? Where second order systems would never get there, a second order system with dead time will get there guaranteed. It's just a case of larger dead time will make it happen earlier. But we are kind of moving away from systems that have indefinite stability with proportional control to having systems with conditional stability with proportional control. So from a frequency domain point of view, therefore, we can kind of say, oh, here clearly visible on the graph is the reason for why dead time is bad for control. From a stability point of view, more dead time will always move us closer to the instability limit. Put another way, adding dead time to a system will always reduce the maximum gain that I can use in my control. put it another way, adding dead time will always reduce the gain margin of my system. Now, I feel this is quite powerful, this idea of saying, well, I can view this from this kind of stability limit point of view. Let me just finish this because what this looks like, dead time ends up looking like this kind of a spiral, right? So the dead time added version of this, if you think about dead time, one way of kind of remembering why that would be the case is remembering that that's what dead time looks like, and then remembering that that is a rotation in the complex plane. And so you can basically imagine that the graph of just that is just a circle, a never-ending spiral. Or it's kind of not spiraling, it's just a circle. Right? And so if your magnitude is going down a little bit, like that'll effectively just take that circle and make it a spiral. So we see in two different ways now that dead time is bad for control performance, right? So we see, the first way we saw this was from just interrogating a simulation where we could see that if we add dead time to a system that will degrade control. We can see that it is possible, this isn't the death sentence to a system. Having delay doesn't mean that we are left with no options. The most common way in which we address the fact that dead time, or all kinds of different delays, because actually there's a general pattern here. Delay is the purest version of this, which is delay is a part of a system that contributes only to the phase. And so you can say, well, it's a pure loss, right? It's not really making anything better, but it's always making things worse. Why is it making things worse? Because it's adding phase lag. Why is phase lag bad? Because it reduces the margins that I have in order to control my system. So it places limits on the gain that I can use. And why is that bad? Because I always want to use the biggest gain that I can, because infinite gain gives me perfect control. So I'm always bumping up against some kind of limit which is stopping me from using this maximum gain that I would like to use, right? And phase is the purest version of that. But you can see that a measuring instrument that has significant dynamics does the same thing, right? So if I have a measuring instrument with a second order or a third order system, that will contribute to phase lag as well. So if I had a second order system in real life and I measured that with a first order measuring instrument, now I have a third order system, and again I'm back to limits being imposed on the gain that I can use. The nice thing about dead time, though, is that it's relatively simple to predict what the response of a dead time free system will look like. If I have a relatively good model of the system, I can effectively just say, well, take out the dead time and use exactly the same response model. From a practical point of view, and there's actually a TUT problem designed around this, so I'm not going to kind of go into that much detail, but you'll see that it can be shown that the structure that you're already familiar with, the IMC structure, incorporates effectively the same kind of learnings from what we're doing here. So I'm going to go kind of in a, this is, let's say, more of a historic thing. It's also, it turns out that this is actually also conceptually easier to implement than IMC. But I want you to, just to be clear, that this technique, which is called the Smith predictor, it predates the development of IMC. Okay, so that's the first thing you need to understand. So it exists in time. You will encounter Smith predictors that are older than any implemented IMC controllers, simply because IMC was developed after Smith prediction. So chronologically, that's kind of the explanation there. The second thing is that these are a lot simpler to implement than IMC controllers, in the sense that they are a purely augmentative idea. In other words, you start with a controller, you have exactly the same controller still wired into the plant, right? And then you say, oh, control performance isn't great. What can I add on? And that's, for me, why it fits well in this section rather than in the control design section, because it follows this pattern of, oh, I had some kind of normal feedback control system. And I have some extra hours or I have some extra money. What can I do to add on to that to make it a little bit better? Right? It's not asking the question of, what could I replace in the system? What could I take out? Like, oh, no, just throw out the PID controller and replace it with a nice IMC controller, right? It's not that kind of strategy. It's an add-on strategy. It's like, I have a controller, it's already working okay, or it's already working at least, it's not completely broken, but I have some extra components, I can add that on. The other cool thing about the Smith predictor is that it requires no additional on-site purchases. So it doesn't require you to install any additional sensors. It doesn't require you to install any additional valves. So if you think about the other stuff that we've spoken about so far, they all require that kind of financial outlay, right? So if I want to do feed forward and I started with the bare basic control system, immediately I'm going to have to stop the plant and install a sensor and so on, right? This is something that is effectively like a software update. You can kind of add it on, mostly because remember, these days you will be either coding or drawing blocks on a screen. You won't actually be purchasing physical units that do this. And so you can kind of just say, oh, I've got this PID system already. I'm just going to add this on. It's going to be in software. It's going to be super cheap. It'll basically take me the time that it takes to run it. So many benefits above IMC. The only downside is that it is a special purpose tool instead of a general purpose tool. So if you understand IMC, you just use IMC for everything. But the downside is that because it's quite a general tool, it's a little bit harder to kind of really comprehend what's happening. There are two versions of the Smith predictor block diagram. The one that I've drawn, or that I've got on the screen over here, focuses on the parts that are that explain how it works. The insight behind the Smith predictor is that I can take the output from the controller and I can use that output to predict what the system is going to do and use the dead time free part of that model prediction to act on. And so in this way, it's almost like the same as a little bit of a cascade, in the sense that I'm acting more earlier on information. It's based on this idea that maybe the problem with the dead time, or the dead time, is from perhaps just a very poorly functioning measuring instrument, or a slow measuring instrument. The classic slow instrument is something like a GC, where you're taking a sample and it's taking 5 minutes to go through the column. So even if you're doing like a continuous GC, you have to actually wait for the stuff to actually travel down the column to settle. There's no sidestepping that. So maybe it's taking a very long time to actually get the measurement out. Now we are doing what is normally done to kind of simplify all the math, which is to say, well, let's just imagine the dead time is just inside of G there. Even if we attribute it to the measuring instrument, we're going to lump everything inside. You'll see it just makes the block diagram a lot easier to deal with. And so we've got this loop here, and you can kind of say, okay, there we have the control output. We feed it in parallel. And if this G is well modeled by G tilde, the model of the system, then in the absence of a disturbance, this signal will always be 0. And this is an important kind of idea behind understanding, or at least verifying for yourself, that this has the opportunity to work, is that I can kind of imagine myself using that system with a perfect model and just having that inner loop, right? So in other words, I've got my normal YSP. Remember, this is 0. I take that, calculate my normal error, right? Calculate my normal error over here based on my prediction of what's going to happen. I then act only on that prediction, and if everything is perfect, if my model is good, I've now just sidestepped. I've got an early measurement of what the system is going to be doing. So that's obviously if everything is perfect. If I had a perfect model, that's kind of how that would play out. Of course, I don't necessarily have a perfect model, and so it's important to understand that all through the calculations that are related to the Smith predictor, you should not allow yourself to imagine that G is equal to G tilde, except in very specific circumstances. So you should carry through. You should never kind of, in your block diagram, allow yourself to say that's equal to G just in the block diagram, because that's not how you build, right? You have to distinguish between the real plant, and I know this is kind of difficult, especially when we're working so much with simulation, but the idea here is that recall that G may not have even mathematical, we may not actually have the actual G. Well, in fact, in any realistic situation, we will never have the actual G. Right? What we have is our best guess of what the model is that describes the system. But in this whole system here, G is actually the real plant, the actual plant that is out there. And what we can do with that real plant is predict its outputs. Another cool thing that you can kind of see from the way this block diagram is set up is, in particular in this block diagram, we're not relying on being able to calculate inverse. So this is also a little bit new. This is different, right? Where we are only assuming that we can calculate a daytime-free prediction. We are not assuming that we can predict or that we can invert the system. We're never calculating the inverse of the system. We're only ever doing a daytime-free calculation. Seen another way, we're only ever running all of these models in the forward direction. And as you may know, it's a lot easier to build forward causal systems than to build inverses. In some cases, the inverses may not exist. In this case, we are guaranteed it doesn't matter. G could be any kind of system. And in fact, not only can it be any linear system, in other words, we don't have to worry about whether it's invertible, we don't have to worry about how high the order is or anything like that, right? We also, in fact, for the Smith compensator to work, don't even need it to be linear. And if you look at the model shape, it's obvious how you would use a nonlinear model in this structure. So if you had a high-resolution nonlinear model, this structure, this block diagram tells you, oh, well, you just simulate what that nonlinear model, you take the nonlinear model, you simulate the nonlinear model's response to the system, right? And you still do all the same math. You still subtract, you just act on that nonlinear model response as though that was the measured variable, instead of acting on the actual measured variable. So it's quite cool, because it means you could, in principle, easily substitute a nonlinear model. It's the first time that we've seen that kind of thing happen. That hasn't been the case for any of the other strategies that we've used, except for feed-forward without time delays. You'll remember that we could use feed-forward without time delays. We could use nonlinear relationships quite easily there, because we could solve those equations. So these two techniques are the only two techniques that we'll do in the entirety of the course that allow us to accommodate easily or incorporate easily the effect of nonlinear process models. So if we have one, the Smith compensator and the and steady state feed forward are the only techniques that you know right now that could possibly benefit from having a nonlinear model. All the other systems, we require that you linearize that model up front. So, very, very cool. Okay? Are there any questions about how the system is working? Right? Because I can demonstrate that it works by showing you the simulation. Right? So we can basically run the whole simulation again. But now with the Smith predictor in place, and what we will find is that the Smith predictor allows us to get almost exactly the same set point tracking response as we had without dead time. Now that doesn't surprise or shouldn't surprise anybody, because in this case we're working with a perfect model. And so with the perfect model, what we basically see is the set point response is simply exactly the same set point response but delayed. Now remember, we can't get away from the fact that the measurement is delayed. And what I'm plotting here is the actual output, or the delayed output. And so from the point of view of this inner loop, right, the set point is happening, the system is responding immediately, and what we're basically seeing is the dead time free response in terms of the controller. So we're using the same settings. Is everybody with me? Right, so we're using the same settings for the controller. All of this stuff is 0. And we're just responding on the error, which is calculated based only on the model. Our model is perfect, and it's just like we're running our simulation without dead time. Of course, it's not all perfect, right? Because remember that there is an opportunity for a disturbance. And so you can see that the system with the Smith compensator does worse than the dead time free system. So remember, this is now using exactly the same controller. And I told you, this is like the cool thing about this, where I can use the same controller. I don't detune the controller. I don't go back to it and kind of try and make it better. I just pretend that the system doesn't have dead time and tune the system that way. And I kind of get the same set point tracking response that I would get in a dead time free system, given that my model is perfect. However, because I don't have a model that predicts the disturbance, right? Because I'm using my model only based on what the controller is doing. And remember, the controller is special because in my system, if I were writing software, I would know everything about the system. So I would know that the controller had output a particular output. I would know all of that. Those values would be available to me. Remember, conceptually, the disturbance is not available to me. I may not even measure the disturbance. I'm simulating it here, so I know it, but it would be cheating to allow the system to see D. Does that make sense? And so the system has to wait for that disturbance to be felt all the way through to there. And so in this particular case, our disturbance transfer function is delay-free. But you can see that if there are dynamics in D, that is unavoidable. There's no way that I can preempt that using just a normal feedback system. Of course, if I had the ability to add a feed forward here, I could improve the disturbance rejection as well. But fundamentally, I will never be able to get away from the fact that the actual system has some delay. And so even with the compensation, the best I can hope for is to get the same set point tracking, because with set point tracking and the perfect model, everything is known to me. There's no unknown stuff happening. Of course, the downside or the flip side is that if there are things that I am not modeling, so in this case the disturbance, the dead time compensator cannot completely reduce the effect of that. So I do get worse performance with the dead time compensator because the model doesn't know, or the model is not exposed to that disturbance. Is that making sense to everybody? So I'm not getting a lot of questions here. Yes?
In figure 15.1,